I posted a video, and the video gives you the hint for chapter 28, programming projects. So if you still have questions, you can email me. Let's now move ahead. We're going to look at an interesting application using breadth first search. We have this model to model the graph and vertices and edges, and we use graphs a lot in a real application, and we use graphs to model the network. We use the graph to solve some optimization problems. And so this one I'm going to show you here is this interesting programming problem. It's the nine-tail problem. So this is, I think I had this problem when I took a team to a programming contest. It was, I think was 1993. So to a regional programming contest. So on the contest, this is exactly the problem. It's a nine-tail problem. So nine-tail problem is this. So you have 9 coins, and so you have 2 heads and tail. So this is the head and tail. All right, so this is 9 in this 3x3 grid. And you can only flip the head. All right, when you flip a head, you flip this head, and also it's enabling cells. All right, so whatever you have, so if you flip on this edge, so you're gonna have this, all this edge flipped, and also this T is flipped. So now see, this is the flip. All right, so now we're gonna flip this one here. All right, now after this, every cell becomes tail. That's what you need. I want to have all this becoming this tail. So this is nine-tail problem, and so here we need to find a solution. How are you going to do this, right? And the solution needs to be the optimal. The optimal means the minimum number of flips. All right, so you can play with this yourself, and you just get a random state and try it. And so you can probably spend hours and without getting any solution. Okay, you just try it, see if you can get anything. It's really difficult because there's so many combinations, and you can just get into the dead end. It's not possible. So we need to write a program for this. So the program will give you a solution and also give you the optimal solution. So the way we do it is now to reduce the problem into a graph problem. All right, so you know the problem, and this is the visualization of the problem. And we now going to solve this problem by reducing it to a graph problem, and we're going to use the breadth first search to solve the problem. So what we're going to do is to look at all this patterns. So you have the combinations, you have 9. So there's each cell is either head or tail. And so you can have all this 9, and all this, we can use this as the, for simplicity, it's actually very good. We're going to use this as 2 states, head and tail. So it's using 0 and 1. So we're going to use 0 means it's head, and 1 means it's tail. So you can see all this possible patterns. So we have this all count all this together, it's 512 nodes. So, and each node is also a vertex. You consider that's a vertex in the graph. So this is all zeros, and this is all zero except this last one is 1, and this one here is, this one is 1, and here is 1 1. So you can see, actually, if you put all these numbers together, so this is 9 bits, so 0 0 and 0 0 and 0 0, so 9 bits, and this is 0, and this is 1, this is 2, this is 3. The last one, it's 5 11. So this is 1 1 1, and then another 3 1 1 1, and another 3 1 1. So that's the binary with 9 ones. That's decimal. It's 5 11. All right. This really helps when you write a code and you can simplify it. You don't have to store this into the two-dimensional array, and you can just use the number representing it, because you know that when you have this number 3, it has to be this pattern, and this number 511, it has to be this pattern. All right, so now we're gonna go look at, these are all the possible patterns, and you can also say this is our possible states. You can get from one state and transfer to another state by doing one flip. So here, we're going to look at this one right here, this diagram. So you're going to see this diagram here. We have this is the one. All right, so this is the 56 in decimal. It's corresponding to binary. This is 0 0 0 and 1 1 1. It's 0 0 0. So now when you do a flip, so which one are you going to flip? If you flip this one right here, flip this 0 here, this is the head, you can only flip a head. So flip this 0, it becomes this 1 1, and this becomes 0. So this is corresponding to this. It's a flip, it going to this one right here, and that is the number. It's now this one, it's 408. It's very easy. You can write it, it's a very simple program to convert this binary into decimal. So this is the decimal is 408, and vice versa. You can convert a decimal to a binary with 9 digits like this. All right, so now this is the one flip. You flip this, the first one 0. If you flip the second 0, it becomes this one here. It's 488. All right, so this, how many possible flips you can have? 6, because you have 6 zeros. Each 0 can be flipped. So flip it into this. All right, so this is showing you here, this is the all this possible flips. Okay, and now you come to this 488. So for 488, you flip this one right here, the last one in the middle, and then you're gonna get into the final state. This is the target you want to reach. It is 511. So you can build a graph with all this edges. So the edges, we use the direct edges. See if you can flip one, so flip a cell here, 0, okay, and flip, well, when you flip one, it's usually all the neighboring cells are also flipped. So you from one pattern, you get into the next pattern. So this is the edge, and the next pattern, the edge is from next pattern to this. All right, so here, like this one, you flip this, the middle 0, and you get to this. So there's an edge. All right, now here, you flip this, the middle in the last row 0, and you get into this. So you can think about the graph with 512 vertices, and then the edges are created. And this way, if there's, you can flip from one to the other, and then you have edge from the other one to this one. So, and this is the graph. We're going to find the shortest path by doing a breadth first search from the root. Root is going to be 511. We're going to start from 511 and build a breadth first search tree. So then you can have the path from the root to any vertex, and that's going to be shortest path using the breadth first search. All right, so here we have the idea now. We reduce the problem into a graph problem and to solve it and using the breadth first search. So we need to write all this code, and so put all this into this. So this is the idea, then we design it. So we design it. This is what we're going to design. We design with this 9-tail model. So this is the model here. So we're going to have the tree. So here is the tree. It's the search tree. We're going to get the search tree. All right. So this is the 9-tail model. And so what you need to get is, it's going to be a shortest path. So from any vertex to the root. So this is the shortest path, and that's actually coming from root to this vertex. So that's the shortest path. It's going to be the solution. So, and this is, you're going to need to build this model, you need to build a graph, right? For this graph, you also all have the vertices, 512 vertices. And what about the edges? So you have to do creating all the edges and create a graph. And so here we have this given index like a 511. So what is that's the corresponding the pattern. So that's, we're going to get the node using the index, and this is the get index from the node. So if you give me the node, so this is the pattern. So with 0 and 1s, so in this 2-dimensional grid, so this is getting the index for it. So that's actually getting the corresponding the decimal value. So here is you're getting this this is the pattern, and this is the index 3. So 0, 1, and all the way 511. So this is indices. All right, so here we're going to flip a node. So when you flip a node at this position, so it's this is the it's the flip the node at the specified position and return the index of the flipped node. So what will be the flipped node here is, so you're going to flip, if you flip from here, so from here, and you flip this, the first row in the middle, so you get this, right? So this, it's going to be index return. This is the 488. So if you use this and you flip at this position, so this is here. And then flip, this is flip a node. And here you're going to flip a specific location, the cell. It's at this index, row index and column index, and in this 3x3 dimensional, 2-dimensional array. All right, so here's a print node. So here's the model. We have built the model. Then we're going to use the model to solve the problem. So you can do some tests. We're going to write the code, just the text-based code. So you're going to enter here. This is the pattern. So H, H, T, 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 H, H, H. So this is 9. So it corresponds to this one here. So if you start at the beginning, so this is the corresponds to this here. So H, H, H. So you see T, 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 H, H, H. All right, so you run the code. You're going to see this is initial state. So you're going to start from this initial state you entered, and then you can see the next here, and you flip this. The one is actually you're flipping is this one here. You flip to this, and then you get this here, right here, and then you flip on this one here, and you get this. All right, so if you change something here, let's change it to T here, and run the code again, and you're gonna see, and here is the solution. It's the new solution. Okay, so here's the solution. Here's T, H, 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 T, 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 H, H, H. So now see here, this is how you're gonna flip it. So how do you get this one here? It is because you flipped the this one here. Flip this H, so it's becoming T, and this one here, it's T, and this one is H, and this one is H. So you can see how it goes with from each pattern. And finally, you get to this pattern. So this is the optimal solution. Okay. You can play with this using this as an example. So enter this H, T, H, T. So you can enter this. You can open another tab, and you can look at this. So write down this T, H, T, 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 H. So you can enter this and put it here and run it, and then you go back and to use this graphic user interface and to see how you get to the final and every cell becoming a tail. All right. So we have this design model, and the let's just look at things here. We already know that we have 0 1s representing H and T. Okay, so this is all the H here, and all 0 here, and all T here, and all 1 here. So now this is the one here, H, 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 T, T, T. So this is 9 characters. So you can use this 9 characters. Here is the or the node. Instead of using 2-dimensional, it's easy. We just use 1-dimensional, and we can find out in the actual location. So this is easy to convert it from 1 dimension to 2 dimension. So that's easy to write a code here. This one. Okay. All right. So this is the 9-tail model, and we write the code here. So the reason I have this protected is later on in the next chapter, we're going to use another version of 9-tail problem. It's called a weighted 9-tail. So we're going to extend this 9-tail model, and we're going to access this search tree. So here, and this one is the tree. We're going to get this tree is this is the so it's unweighted graph. Okay. Well, let me put this on. I'll just go get the answer here. And so you're going to see this here. I'm going to do this. Yeah. So here's unweighted graph. The vertices are integers. So 0, 1, 2, 3, all this as index, and in search tree. So this is the constructor to construct the model. So you get all the edges, and now you use this constructor and all the edges, and this is number of nodes. Number of nodes is 512. So the vertices are the numbers starting from 0 to 511. So using this constructor, and then this is to get the breadth first search tree starting at this, the final vertex. It's 511. So you can read the code, see how you get all the edges, and so please take your time and to look at how you actually code it. All right, so now with all this, you can write a test program to solve this 9-tail problem, and to use this model, you build this model here. So this is 9-tail model. You have this model, and then you from this model here, and you already have a tree there, and the breast fossa tree. So all you need is give me any input S. It's entered as a string. So this is as a string, and you can get this array. So this is initial. This node is array, and from this is all the characters, and you can get the index. So this model. So here's get path in the model here. So you get this path, and this path as a list, and you can print this all these nodes on the list. So this is 9-tail model that print node, and then for this is you get the node here, the index for each node. But get the node given the index and on the path, so you get the node. So this is all the nodes here, the nodes printed. All right. I think that's all for this chapter, graphs and applications. So we're going to see this is the data structure, how we design new data structures. And this is the data structures when we design this new data structures, and we use existing data structures here. See all this, we use the lists, we use array lists, and so when we implement the algorithms here, the depth first search, and we use recursion, it's a stack. It's if you don't write code using recursion, you have to use a stack. And for the breadth first search, and we use data structure, is the queue. We use the queue, and in Java there's no concrete class queue, so instead we use linked list. And see the choices. And if we don't use linked list and we use array list for breadth first search, and your program is still going to work, but it's not going to be efficient. So for this breadth first search, we use a queue is because it's first in, first out. So you're going to have to remove things from the front. So that operation, if you use a linked list, it's out of one time. If you use a array list, it's out of n time. So in this class, we introduce the classic data structures, and that are universal. It's all in all the API languages, and Python, C++, and Java, and other languages. You all have all these data structures. The data structure is very similar. You just have to use it in the right way and to get the efficiency. All right. So in the Java API, the data structures are defined using classes. And when you create your own data structures here, now you see you have the classes here. We have the class here for modeling the graph. And we're going to see this is unweighted graph. In the next chapter, we'll look at weighted graph. So in the overall design architecture, we're going to have to make the weighted graph as a subtype of the graph. So because weighted graph, you're going to add additional property, that's weights. All right, we're going to see that weighted graph in the next class. We're going to start to introduce chapter 29 on Wednesday. All right, any questions? Okay, so if you don't have any questions, and feel free to leave. If you have questions, you can stay. All right, thank you. Bye.